Hello and welcome to this week's review video. Last week I talked about a scaling down method of logic devices, the method being strain engineering. In strain engineering, we improve the carrier mobility in order to achieve a better current throughout the device. Well, this week we'll be looking at high K metal gates, high K dielectric metal gates. First, I will be talking about the first part, the high K part. The high K metal dielectric was implemented to achieve a better gate controllability in our short channel device. As you all know, the short channel effect is caused by a weaker gate controllability as the device size decreases. So, in order to increase the gate controllability, we make our oxide capacitance C-ox much more stronger. And as you know, the C-ox equation is the permittivity of the oxide divided by the oxide thickness. However, the easiest approach is to have a more thin device to achieve a better C-ox, but however, as the oxide becomes much more thinner, the quantum tunneling occurs. And when the quantum tunneling occurs, the tunneling electrons makes a leakage current, and the leakage current leads to a more power consumption and poor device performance. So the only solution is to have a better permittivity on the oxide, and that better permittivity is the high K materials. Now, moving on to our metal gates. The first question about the metal gates is why do we implement metal gates? And that's a fairly good question. I first questioned it too. Poly SIs are pretty good at their jobs, but however, there's some few problems with the poly SIs. The first problem is the polygate depletion. The polygate, no matter how we dope it into a metal, it's still an Si, it's still a semiconductor. So it tends to deplete on the interfaces on the device. So, and as we all know, unwanted depletion region in the device leads to a poor performance. And the next problem is the dopant penetration, boron to be exact. Borons are extremely light. They have a atomic number 5, so they penetrate the device and makes a interface traps, and we all know that bad device. And the final problem is the Fermi level pinning. Now, the Fermi level pinning is a complicated subject in its own right. So, to put it in a nutshell, all the materials has their own surface states, and when different surface states meet, those energy bands, energy states, tends to stuck or fix at certain points, hence Fermi level pinning. Now, when the Fermi level pinning occurs, the energy bands, the energy level, won't budge because it's pinned, and the energy level pinning makes it hard to make a VT adjustment throughout the device. So we need to have a metal gate instead of polygate to achieve a better VT adjustments. Finally, I will talk about some precautions on the Hkmg, high K metal gate implementation. The first being interface states. Again, now when the interface properties between two materials are bad, the interface traps seems to occur much more often, and we all know that interface traps lead to a CIT and again bad device performance overall. So we need to take notice of interface states. And next, the final precaution is the thermal budget. High K materials are really vulnerable to heat, so we need to check the thermal budgets of our processes. And that will be it. Thank you for listening. This has been Myung Kim.